it's working. All right, here we are. We are live, everyone, live. This is National Gourmet Coffee Day, 1/18/2017. G-O-U-R-M-E, the gourmet way to spell gourmet. In fact, the only way to spell gourmet. All right, factoid of the day. Example 8, here we go. You'll have a question like this on your quiz tomorrow. It says if the natural log of 2 is about 0.7, and it is, it's really like 0.69 something. Have y'all heard of the rule of 70 in any of your science classes, social science or science? The rule of 70 tells you basically approximately how long it's going to take for a population to double in size given the percentage growth rate. It's 70 divided by the growth rate. So if a population grows at 3.5% every year, then about how long will it take to double? What's 70 divided by 3.5? 20. Good. So it'll take approximately 20 years for that population to double. Okay, that's the rule of 70. And the rule of 70 comes from the fact that 70 is about 0.693, and 0.693 is the natural log of 2. So the 2 in the natural log of 2 is where the doubling comes in. But that's just extra information. Right now, we just know that the natural log of 2 is about 0.7, and I want to be able to express the natural log of 8 then as approximately something. Now, the reason that I can't get it exactly without a calculator is because if I say that equals x, and we convert it by exponentiating both sides, e to the natural log of 8 is 8. Can you write 8 as a power of e? E is irrational. It's 2.718, blah, 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 and 8 is an integer. So you're not going to be able to express 8 as a power of e. Now, we do know that it should be about what? E to the first is bless you, where bless you equals 2.718, and that's too small. E squared is going to be, well, it's about 3 squared, which would be 9-ish, so a little bit less than 9. So it might be around 2-ish, maybe a little bit less than 2, maybe a little bit bigger than 2. But it should be 2-ish, all right? But we're not sure. So without a calculator, the only way we can maybe come up with an approximation is to realize that the natural log of 2 is about 0.7, and now can we express 8 in terms of 2? So that's what this comes down to. And the answer is, heck yeah. So working straight down, 8 is the same as 2 cubed, yes? And now we can use the properties of logs, namely property 3, that says exponents on arguments can come out front and become constant multiples. So we can write that as 3 now times the natural log of 2. Sweet. And now I can replace the natural log of 2 with what is approximately equal to natural log of 2, and it's 0.7. Now, here's just kind of a little notational heads up. When you work straight down, you're basically assuming or inferring that every line that precedes or follows is equivalent to the one above or below. In other words, it's almost like putting equal signs here. But you don't need equal signs. It's implied that they're equal. But as soon as you replace something with something that is truly not equal to it, but rather only approximately, now it's incumbent upon you to put the squiggles. So that is now going to be approximately 3 times 0.7. No, that's my next thing. 3 times 0.7 now is actually not approximately 2.1. It is 2.1, right? What is 3 times 0.7? About 2.1. No, not about 2.1. It is 2.1. So, again, if it's an equal sign, you technically don't need it. So you don't put squiggles every single time. You put it one time. And it's just the time where you go from replacing something that's only an approximation of the previous line. And, of course, the equal signs are inferred everywhere else, but if you want to have them there, that's fine. So the answer is 2.1. So guess what the natural log of 8 is? It's about 2.1. Now let's see what the calculator will tell us. Natural log of 8, please, Siri, Alexa, Google Dot, Echo, whatever. 2.079. If you round up, it's about 2.1. So not bad, not bad, not bad. Way to go, calculator. Way to go. Was that hard? No. Was it fun? Yes. Was it easy? Yes. It's been easy. All right, do the same thing with the natural log of 1/4 on your own. I'll give you a minute. Did you get negative 1.386294361? You should not have. You should not have. Because that's not what the answer is to example 8b. So again, the natural log of 1/4, I can't write 1/4 as a power of e. But if I can write 1/4 as a power of 2, knowing that 0.2 is about 0.7, I can get a decent approximation. So I'm going to show you the baby steps, but I want you to practice going straight from where we're at now, the natural log of 1/4, to where we're going to end up here. 1/4 is 1 over 2 squared, right? And now, if you could bring the 2 squared to the top, what do you do to the sign? Change the sign of the exponent. So that's 1 times 2 to the negative second. And of course, 1 times anything is itself. So what I would like you to be able to do, and this takes a little bit of practice and a deliberate mental effort, is just to think of 1/4 as 2 to the negative second. They should be synonymous with you now. Now that you've written it as a power of 2, now you can use the properties of logs. And again, kind of similarly, we'll bring the negative 2 out front and it becomes negative 2 natural log of 2. And now because I've isolated the natural log of 2, I can replace it with what? 0.7. So what goes on the next line in front of the expression? Squiggles. We can call it squiggles. Squiggles. Like the worm candy that's sweet and sour. You ever eaten those? They're good. They call them squiggles. So this is negative 2 times 0.7. And now negative 2 times 0.7 is equal to negative 1.4. So the natural log of 1/4 is about negative 1.4. And the calculator will tell you that it gets negative 1.38. And I typed it in 3 ways correctly and one way incorrectly. All right. Letter C. Do C and D. No, do C. Do C. I'll give you 30 seconds now. Yes. If you are not of legal age, I think 18 or older, then you have to have some pre-approval from a legal guardian. Yeah. So the calculator tells you that the actual answer, or at least as many decimal places as it's showing, is 0.346573593, which is a less popular Tommy Two-Tone song. 0.34656735903. Okay, it didn't take off as well as the 8675309 song. All right, so let's go ahead and write this as the natural log of 2 to the 1/2. The 1/2 then slides out front, and we get the natural log of 2 times 1/2. And now what goes next when we replace natural log of 2 with what's it's only approximately equal to? Squiggles, 0.7. And of course, half of 70 cents is 35, right? Unless you take your 70-cent coin and cut it in half with 10 snips, then it's worthless. Okay? 0.35. And that's pretty close to what the calculator said, right? Yep. And then this one here, log base 4 of square root of 8. Oh, my goodness. Okay. Okay. What's different about this one? There's no ln, right? So if I know that the natural log of 2 is 0.7, then if I'm trying to approximate this, in order to use the natural log of 2, I should probably think about doing something with log base 4, yeah? Is there a way to convert log base 4 to, oh, I don't know, another base? Like change it somehow by way of some formula? Change of base formula, exactly. So let's do that first. The change of base formula says we can take the log of any base, I'm going to choose base e, the natural log of the argument over the natural log of the base. Change of base formula. Log of the argument over the log of the base. And now, since I'm dealing with logs, now my goal is the same. I want to write the square root of 8 in terms of 2, and I want to write 4 in terms of 2. And then if I need to, then I can replace the natural log of 2 with 0.7. So here's where, again, I want you to be able to do this in one step. The square root of 8 is the same as 2 to what power? 3/2. Good. The square root puts a 1/2 exponent, but 8 is 2 cubed, so 3 times 1/2 is 3/2. The bottom, the natural log of 4, becomes the natural log of 2 what? Squared. So I want you to be able to go straight from 4 to 2 squared. Good. Now, when we're working vertically, we want out of room, just make another column. Now you can use actually the properties of the logs, property 3, to bring the coefficients out front, or the exponents in front and its coefficients. So the numerator becomes 3/2 natural log of 2, all over 2 natural log of 2. And now I guess we could replace natural log of 2 with 0.7, unless there's a way around it. Yeah, in this case, it's a factor of both the top and the bottom, so they divide out. Nice. And you end up with 3/2 halves. What's 3/2 halves? Is it 6 halves or 3/4? Oh. Well, when in doubt, stay, change, flip, right? Put the 2 over 1. Stay, stay, numerator, stay. Good numerator. Change, flip. And now you multiply straight across and you get 3/4. Did I need to put the squiggles anywhere here? Nope. Because the natural log of 2's, which I was going to approximate, they divide it out. So the log base 4 of the square root of 8 is indubitably 3/4. Now, knowing that you didn't need the natural log of 2 approximately there's other ways to do this problem, right? And we've done that before. You could have set it equal to x. You could have converted it then to exponential. And then you could have gotten the bases the same on both sides, both as powers of 2's. And then if you equate the exponents, you get 3 equals 3/4. And that's what's so fun about logs. There's many, many different ways to do every single problem. And as long as you're not breaking any mathematical rules, if you keep chipping away at it, you'll end up with David, the statue, okay? Which is what Michelangelo did. All right, let me give you a bonus one. We'll call this example 8, example 8b, capital B for bonus. If the natural log of 5 equals A and the natural log of 2 equals B, write the natural log of 200 in terms of A and B. That would be more like a quiz question tomorrow. So take 1 minute and do that, and see what you get. By the way, if you haven't tried the seafoam color on the Notability, it's pretty cool. It's a good color. It's under the new palette. Although maybe I'm using the wrong seafoam. I guess this color of seafoam depends on which disgusting part of the sea you're in, right? Ooh, that's seafoam. Gross. That sounds disgusting. You know what's more disgusting than seafoam? Hotel pool foam. There's not a color for that. It usually kind of collects in the corner. Gross. All right, what'd y'all get? 5.298? If you did, you cheated. Because that requires a calculator, number one, and number two, it's not in terms of A and B. But that's what it's equal to. So the key here is, once again, to write 200 in terms of 5 and 2. But instead of saying that it's approximately a specific number, we're just saying call it equal to A, call it equal to B. So it comes down to this. Get the prime factorization of, in this case, 200. Because notice 5 is a prime number and 2 is a prime number. And if you can write then 200 in terms of 5 and 2, then you can write it in terms of A and B. So however you want to get it in terms of its prime factorization, whether you want to do factor tree, upside down birthday cake, or if you just realize that 200 is 2 times 100, and 100 is 4 quarters. I know that because I'm good with money, right? And so that's going to be 2 times 4, which is 8, right? So 8 is 2 cubed, and 25 is 5 squared. So again, however you want to get to the prime factorization. Factor trees are fun, right? Upside down birthday cake is fun. But get the prime factorization. So now 200 is the exact same thing as 2 cubed times 5 squared. Now you can use the properties of logs. The first thing you want to do is expand the product. It becomes the sum, natural log of 2 cubed plus the natural log of 5 squared. And then using property number 3, the exponents can slide out front. So it becomes 3 times the natural log of 2 plus 2 times the natural log of 5. And now, finally, you can replace the natural log of 2 and the natural log of 5 with the correct letters. So be careful here. The natural log of 2 is not approximately, but I said is equal to which letter? B. You don't want to do it correctly here and then make the wrong substitution. 3b plus 2a. That would be the final answer. So this makes a great multiple choice question on a test. 3b plus 2a would be an answer choice, and guess what else would be an answer choice? 3a plus 2b, for the person that just substitutes incorrectly at the end. So make sure that that's not you and maybe someone else. It's not your job to make sure it's not someone else. But if it is you, don't make it someone else. Keep your work covered with your cover sheet. All right, so that one, you'll have one like that on the quiz tomorrow. Any questions on example 8? Okay, so here's a nice little application of logs, and there's lots of applications of logs in the science and in the social sciences. If you have Mr. Kilford, or you have had Mr. Kilford, he talks about the social scientist Mr. Ebbinghaus. And there's a rule or a log that he came up with that he named after himself called Ebbinghaus's law of forgetfulness, or forgetting. And basically what he said is that if you master something at a certain level, and we can call it like a percentage level. So like if you study logs and you practice logs, and next Tuesday on the log test you make 100, right? Over time then, if you don't keep practicing and you don't rehearse, he says that over time then what's going to happen, do you think? You're going to forget, right? Not everybody goes home after the log test next Tuesday and for the next year goes home and practice logs. Oh, my alarm just went off. It's time to go practice my logs. I'm going to go practice my logs, my daily practice of logs. And then I'm going to go ahead and record the results of my practice in what I call my log. Okay? Very few people do that. So over time, if you don't keep rehearsing, you tend to forget, right? Unless it's riding a bicycle. It's like, I haven't ridden a bike in 3 years. Well, get on, see how it feels. Oh, yeah, it's just like riding a bike. That's why the idiom works, okay? No one forgets how to ride a bicycle. What is this thing for? Apparently, you never forget how to ride a bike. But most things, without rehearse, you forget. So here's what he says. If you learn it at a performance level P sub O, so this would be like for our purposes, it'll be like your initial grade or your mastery level percentage, okay? Then after a time period of T, and we're going to measure T in months, it says that later. So if you let T months go by without rehearsing, then you're going to be performing at what we call now level P. So P is going to be your level at time equals T. He came up with this equation that models that. And notice it's a log equation. And it's base what? What's the log? Base 10. So scientists, social scientists, they typically use base 10. But math, we like to do things differently. We like to use base E. Now, because it's a log equation, here's kind of what it looks like. How did he come up with that equation? Probably the same way Kekulé came up with the configuration for the benzene ring, right? In his dreams. Or if not, he probably collected data. You get people come in and you teach them something, and then you assess them and you say, hey, come back in 10 seconds and we'll do it again, and then come back in 10 minutes and we'll do it again, and then come back in 10 days, 10 weeks, 10 months, 10 years, and we'll do it again. And you're like, God, I didn't realize this was going to be so involved, having to keep coming back. If you ever take psychology in college at the freshman level, guess what one of the course requirements usually is? You have to actually go be a guinea pig for graduate students at least once, maybe even twice. It's part of the course requirement, where you go into the little social scientist lab and you sit in a little room and they perform these experiments on you, and they use you as a guinea pig, which is kind of insulting, especially when they set the little carrots next to you to snack on while you're doing this. But anyway, so that's how they collect data now, and it's a requirement. But anyway, you can collect data, and once you plot the data points, you can actually have your calculator, believe it or not, will fit a curve to it. And there's ways to establish what type of curve will capture the variability of the data points. It's called the method of least squares regression is one way to find the curve, and it was invented not only by no other than Johann Carl Friedrich Gauss, one of the best three in the world. But anyway, here's what the curve looks like. If you let time go by and you let your performance level in percentage be mapped on the y-axis, over time your performance is going to decrease. So let's look at how it could decrease. It could go down like this, and we'll call that one green. It could decrease like this. We'll call that one the red one. Or it could decrease like this. We'll call that one the sea foam. Those are all decreasing over time. Which of those three different graphs do you think Ebbinghaus exhibited when he plotted his scatter plot data points? The blue one, the green one, or the red one? It's the red one. Yeah, because the red one is the one that looks loggy, right? It's the one that looks loggy. So if you get rid of the others, this is a log equation. And remember what logs do. This would be logarithmic decay. They taper off. Okay? They taper off. So you're going to lose a lot of information in the beginning, but over time, you're still losing it, but less and less. And I guess that's because there's less and less to lose, right? Yeah. So that's, anyway, he plotted these data points, you know, from his study, and he fit a curve, and it came up like this. So let's look at it. Log of P sub O minus C, log of T plus 1. T is measured in months. C is going to be the Ebbinghaus constant. Okay, and that's going to depend on the task involved. People are going to forget how to manipulate log expressions at a very different rate than they're going to forget how to ride a bicycle, okay, for example. So the C depends on the task. Let's look at question A. It says solve for P. Solving a formula, or a literal equation as we call it in mathematics, for a variable is a very important task. You're manipulating expressions that have variables in them, and depending on how many calculations you want to do, you might want to solve this for P, you might want to solve it for C, you might want to solve it for T. Okay? We call this a literal equation, also known as a formula. All right, so let's solve it for P. I'm going to go ahead and rewrite this, call this part A. I get log P equals log of P sub O minus C log of T plus 1. Now, the quickest, fastest, easiest way to solve for P, which is right here, is just to unlog both sides base 10, right? So you can immediately raise both sides to the, or exponentiate base 10. Now, look what happens. On the left side, 10 to the log base 10 of P is just P, and then you get 10 to the, holy moly, you get all of this right here. Log of P sub O minus C log of T plus 1. Now, what I would do is I would recommend putting that in parentheses because that is a huge exponent. And those last terms are cantilevered way out there, and you don't want them to fall down on the ground floor. Now, that met the requirement. We did solve for P, but it's still not the most useful version of P. Because if I were to plug something in, I would still have a lot of evaluating to do in the exponent. So if this were a test question, and I said, which of the following is this equation solved for P, that would not be an answer choice. So let's not do it that way. All right, so what I'll do is I'll just kind of keep a record of that. No, I won't. You can put that off to the side if you want. What I'm going to do instead is focus on this side, because remember, that was the exponent. Let's see if we can simplify that first. We want to make this formula as user-friendly as possible. You have a log minus a log. They're both base 10. What can we do there, log minus log? Yeah, we can condense it, right? Now, the first step in condensing is to make sure your coefficients are a 1 and negative 1. I have a coefficient of C right there, so that needs to come up as an exponent. So the first thing, and I'll do this in baby steps, is log P sub O minus log T plus 1 to the Cth power. And that's still equal to log of P. Now I can condense. The right side is log base 10 minus log base 10. So when you condense, remember, you pull one log out front. If you have a negative term, which we do, you know you're going to have a denominator, so build the shelf. The positive term's argument gets multiplied in the numerator, so that's P sub O, and the negative term's argument gets multiplied in the denominator. So that simplifies the right side. Now the left side is still log of p. And now it makes sense to unlog both sides by exponentiating base 10. Or using the fact that logs are 1 to 1, you can set the arguments equal to each other. But it's fun to exponentiate. So what is 10 to the log base 10 if you want to write the base there? What is 10 to the log base 10 of blob? Blob. So in this case, it's p on the left, and on the right, log base, or 10 to the log base 10 of blob is the blob. So we get this. Now, isn't that a much better looking formula? Why? What do you notice about it? There's no logs, which would be exciting to most people, but kind of disappointing for that one person that's practicing their logs on a daily basis. Now, how do we know that it's still related to logs? How do we know it still kind of has the genetic DNA of a log? It's exponential, right? C is the exponent. But notice it's a lot easier to use because we don't have to evaluate using logs. So this would be a really good version of the formula if you wanted to find the performance level P somewhere down the line as a function of T. In fact, it is a function of T now. So if you want to write that as P of T instead of just P, it is a function of T because C is a constant and P sub O is going to be a constant too. All right, so let's go ahead and answer part B. Assuming on part B that you scored a 90 on your initial test. So if you make a 90 next Tuesday, are you okay with that? You shouldn't be. Okay? No, it's not. No, it's not. If you're content with a 90, you're in the wrong class, right? So why did you miss 10 points? We could talk about that at some other time. Okay? Maybe you're happy with it because you didn't study, right? Or you had a bad night the night before. But if you did your job and you prepared and you walk in and make a 90, you should be disappointed with yourself. Okay? Be upset at yourself for a little bit and then use that as a fuel to fire the furnace that propels you forward to do better the next time. Yeah, it's all relative. But you haven't mastered it, right? The state of Texas and our district sets passing at 70. But in your own mind, maybe 90 is failing, right? Okay. So if you make a 90 on your initial test, and then you wait, what does it say up here? We're going to wait, what would you score after 2 months? So if you wait 2 months and you come back in, they do tell us the C value here, which is good because I have no idea how the C value is actually calculated. But in this case, for this example, a log test, maybe C is 0.2. So what do you think? You make a 90 on the test next Tuesday. You come in 2 months later, and remember, you're not the person practicing logs anymore at home. What do you think you're going to do on that test, a similar test? And to be similar, not the same, because then you can just memorize, and that's not an accurate indication of knowledge. You think you're going to do the same, better, or worse? It's going to come back to you, right? Yeah, now the C value kind of takes that into consideration, right? If logs are your things, then you're going to have a different C value than someone else who's like, logs are torture, okay? And then maybe when they finish, they try to deliberately, bury it in the recesses of their mind. It's a coping mechanism. You're probably going to do worse, according to Ebbinghaus, right? Because you're going to forget a little bit of the log stuff. So let's go ahead and plug it in. Our performance level, P, then, is going to be 90 all over 2 months plus 1 to the Cth power, which is 0.2. And now it's time to go to the calculator. So you do it on your calculator, I'll do it on mine, and we'll see if we come up with the same answer. 90 divided by 3 to the 0.2th power. Fun to say 0.2th power. 72.246, which, of course, I will truncate your grade so you don't get a big head about yourself. I will just call that a 72 instead of a 73. Okay? But you're a nice teacher. Can you give me a 73? No, I'm not. So you're still passing, right? Quote unquote passing 2 months later. But what happens if you wait 1 year? What if you come back a year later? Well, first of all, units matter. So a year is how many months? 12 months, unless it's a leap year, and then it's what? Still 12 months. Yeah, not 13. Leap years don't work like that. So let's see what our performance is a year later. All right, you come back to visit me like, hey, Ms. Scorpio, I'm in college now. Okay, good. Sit down and take this log test. Hey, wait, I'm just visiting. I'm collecting data. Here's some carrots. All right, so 90 all over 12 plus 1 to the 0.2's power. All right. You think you're still going to pass? Oh, I don't know. Don't go visit Mr. Corpy. He makes you take math tests when you visit him. 53.883. Not so good. And, of course, I'm a fan of truncating. Let me come back over here. Notice what I did over here. I put equals 72.246 and equals 72. I just forgot one of my own rules. Speaking of forgetting, what should be here? Should be squiggles. In the presence of the 3 decimal and then the approximate, that would be mathematical prevarication. That'd be lying. Over here, then, I'm just going to say that's equal to 53. Again, I don't want you to get the ego. You know, I didn't do it in a year, and I got to 54. No. You got a 53. Okay, I'll quit bragging. 53 is much worse than 54, just psychologically speaking, right? Okay, so anyway, you can have fun with this. Mr. Kilford will talk about it in class, Ebbinghouse's law of forgetfulness. Over time, you tend to forget things at a logarithmic rate, all right, if you don't keep practicing. All right, now we got 4 minutes. Example 10 is one of my favorites. We're going to look like we did with exponentials, how we can go from one graph to another graph. So to show you how we're going to do that, we want to start with log base 1/2 of x, and we want to end with another log function, but we want to end with y equals log base 6 of x. Now I actually give these guys names, so let's give them the names I gave them. F is going to be log base 1/2, and log base 6 is going to be what I call g of x. So let's think about graphically what we're doing. Log base 1/2 of x, if we graph it, it's a logarithmic decay function. But what these two functions have in common are x-intercepts of 1, 0, and vertical asymptotes at x equals 0, right? That's what all functions of the form log base b of x have in common. But log base 1/2 of x is a logarithmic decay. And what I want to know is what do I have to do to get that graph to become this, which is y equals log base 6 of x. Now, the obvious thing, graphically, is I have to reflect it across the x-axis, right? So to do that, I'm going to have a negative in front of my answer, right? An x-axis reflection means we have a negative a in our standard transformation form. But I also have to tweak the steepness of the graph because a base 6 and a base 1/2 have different steepness. So I'm going to have to actually vertically stretch or compress it by a certain amount to change the steepness. I can't horizontally compress or stretch it because that'll change the x-intercept. So it's going to be some vertical stretch or compression and an x-axis reflection. So here's what I know. I know that log base 6 of x should equal a times log base 1/2 of x. And I want to figure out what a is. I do know that a has to be a negative number because I have to reflect it across the x-axis. But what is the dilation factor? I don't know. So here's how we did it with exponentials, and here's how we're going to do it with logs. You start with your end product. We want to end with log base 6 of x. So just like when you work those maze problems, if you work the way the instructions say and you go from start to finish, you hit a lot of roadblocks. But when no one's looking, if you start at the end and you work your way out, it's a lot easier. It's not cheating, it's smart. All right, so here's what we're going to do. I want to convert log base 6 into log base 1/2. And for that, we're going to use the change of base formula. So log base 1/2 of x over log base 1/2 of 6. Start with the end in mind and convert it to base 1/2. Now notice log base 1/2 of 6 is in the denominator, but it's just a number. So just like x over 3 can be written as 1/3 x, I can kick that thing out to the side. So that's going to be 1 over log base 1/2 of 6 times log base 1/2 of x. And now I'm technically done. This right here out front is now my a value, right? So my a, my vertical dilation factor, is actually 1 over log base 1/2 of 6, which must be a negative number. But on a multiple choice question, I'm not going to leave it in that disgusting form. So now what we're going to do is we're going to focus on that and see if I can't rewrite that in a more user-friendly format. So I'm going to focus just on the A part, the number. All right, I'm going to finish recording this problem. Y'all can walk out if you want to finish the last little tidbit tonight. I'm going to put it in terms of the natural log. No, not this one. Put it in terms of natural log, state change flip. And now the natural log of a half. I'll keep narrating as you go. Have a great day. Natural log of 1/2, we could do a couple of things with. We can expand it. It's the natural log of 1 minus the natural log of 2 over the natural log of 6. And, of course, the natural log of 1 you have memorized as 0. And now y'all are gone, and it just feels like I'm talking to myself. So the negative natural log of 2 over the natural log of 6. And that's a good version of A. Now, there's another way to get from this line to the answer. If you call 1/2 2 to the negative first over the natural log of 6, now you can actually use property 3, which says you can bring it out front, and you end up with that a little bit more forthright. So anyway, I'm recording, so I'm just finishing up. I'm talking to myself. How y'all doing? Yeah. So anyway, to go back to plug it in, we know that log base 6 of x then is equal to the negative natural log of 2 over the natural log of 6 times log base 1/2 of x. And there you go. So we'll flip it across the x-axis. That's the negative. And we'll vertically dilate it by a factor of. Anyone want to say it? We'll vertically dilate the graph by a factor of.
Natural log of 2 over the natural log of 6.
Well done. Excellent. Bye. Yeah, that was Gabby.